Okay. So we I wanted to start one part on the slides, but during the break, I decided that we, first of all, we describe the Snell laws, so we will be ready to go in the laboratory as soon as possible. Now, to go ahead, we give a description of the so-called geometrical optics. And what do we mean by geometrical optics? We said that light can be, or an electromagnetic wave can be represented by its wavefronts. So planes where the phase is constant, okay? And we know that if we have one plane wave that is propagating along one direction, on the planes that are perpendicular to the propagation direction, the field is constant, okay? And this is an electromagnetic view, or classical electromagnetic view. But we can think in terms of so-called geometrical optics, and we can say, okay, we replace the wavefronts, these planes, with optical rays, and these optical rays are perpendicular to the direction of the planes of constant phase, okay? So we can use a representation of an electromagnetic wave where instead of drawing the phase planes, we draw the direction of propagation, okay? No, I did. I think I did. I just check if I am recording. Right. Yes, I am recording. Okay. And so we introduce the concept of an optic ray that is perpendicular to the plane of propagation. So in the Huygens principle, we said that if we have a wavefront, okay, you can calculate the wavefront at a certain time later by the Huygens principle, okay? Now, what we, in geometrical optics, we say is that locally, the optical ray is perpendicular to the surface of the wavefront. And what I am asking to myself, can I represent the propagation of light with optical rays, okay? And of course, the Huygens principle tells me, okay, look, the wavefront at a certain time later will be like that, for example, okay? And locally, the rays will be perpendicular to the direction of propagation. So I will have that if I draw the line that point by point is tangent to the optical rays, I will have that the optical rays will be like that. Locally, this line is the ray line. Normally, it is not a straight line, but light is propagating in a snake-like behavior, depending on the refractive index of the medium. Okay? Now, in principle, this is very difficult to describe, but we will make it very simply. What we know is that if I am in a homogeneous medium, I do expect that the wavefronts, if they are flat, they keep flat. And I do expect that the rays propagate in a straight direction because there is no distortion of the wavefront. Okay? So in a homogeneous medium, the optical rays, they behave like arrows, they go straight. Okay? Of course, in a non-homogeneous medium, the optical rays can behave like speed in a fluid, for example. If you have a fluid, the speed of the particles will follow certain traces. Okay? Now, the most simple problem that I can solve after the homogeneous medium is an interface between two homogeneous media, the most simple problem. Oh, we reached the maximum of pages. So I have to save this and start a new one. I cannot add pages. Okay. So if I want to study propagation of a light ray in an homogeneous medium, the most simple case I can solve is a flat interface between two media with two different refractive indices. So this is an homogeneous medium, this is an homogeneous medium. They have two different refractive indices. And I ask myself, okay, if I have a light ray that is getting from the medium number 1 with refractive index n1, it will propagate as a straight line. What does it happen to this light ray when it reaches a separation between the two media with two refractive indices? I can identify the normal to the interface between the two media. I can identify this angle here as the so-called incidence angle. Okay? And I will have that light will cross the interface, and in general, the light beam will come out at a different angle that I will call T, the transmission angle, and that in general, the two angles are not equal to each other. One part of the light will be reflected back at a certain angle that I call R. So there will be a reflection of light, and there will be the so-called refraction of light. And this is the incident light. Now we have, from basic physics course, the so-called Snell's laws. These are two laws. The first one says, look, the incidence and reflection angles are equal. So the reflection angle is equal to the incidence angle, always. Okay? This is typical if you think that this is a photon, a bullet. When a bullet elastically reflects on an interface, the momentum of the particle is flipped along this direction, and it is preserved along this direction. So a ball in a billiard will be reflected to an angle that is equal to the incidence angle. We don't go into the details, but this is what we know. The second Snell law is concerning refraction and tells us that if you calculate the product n1 times the sinus, the incidence angle, this must be equal to n2, the sinus of the transmitted angle. So there is a relation between the incidence and the transmitted angles, and it's given by this law here. Now, the reflection law is very seldom used. We don't use almost never. While this is used very often. And normally people say the Snell law is the second law, okay? You can write like this, sinus I divided sinus t is equal to n2 n1. Okay, this is Snell law. So what does it happen when a light beam crosses a flat interface between two semi-infinite media? The direction of propagation changes. And the extent of change depends on how much it changes the refractive index. If the two refractive indices are the same, you have the same medium, left and right, the ratio is 1, the two angles are the same, and light goes straight. If the refractive index are much different, the two angles will be much different from each other. Okay? Now, Snell's law is a geometrical law. It gives you information only on the angles of propagation of light beams. Okay? Of course, in your mind, what you have in mind is that physically, here you have a plane wave that is propagating in this direction, okay? And this plane wave is constituted by phase fronts that are advancing, okay? Here you could write that a plane wave is given by an incident field sinus the incidence k vector like this. It is a plane wave. This is the representation. And the reflected wave will be written in the same way. Instead of K1, you will have KR, K reflected. And the transmitted wave will be written the same way. By applying the interface continuity at the field at the interface in electromagnetics, you work out this expression here, but we don't do it. We give it for given. Okay? Now, no, because I have to do this. Okay. Now, so we have sinus I divided sinus R is equal to N2 divided N1. Now, what does it happen if N2 is larger than N1? So what does it happen if you have light that is arriving from this side at a certain angle I, and it is refracted in the second medium, okay? Now you see that if n2 is larger than 1, that means that sinus I over sinus R, that is n2 over n1, must be larger than 1. Okay? That means that this angle I is larger than R. So in this particular case, you will have refraction here, but the transmitted angle will be smaller than the incidence angle. So the light beam, when it passes from a medium that has a lower refractive index to a medium that has got a larger refractive index, is bent towards the normal to the surface. Okay, it's pushed to the normal. Vice versa, if you are in the opposite condition that n2 is smaller than n1, then what do you have? You simply have the opposite. You have something like this. So if this is the incidence angle and this is the transmitted angle, this transmitted angle is going to be larger than the incidence angle. So when you pass from a medium with a larger refractive index to a medium with a lower refractive index, the beam is sent away from the normal. Okay? And now you immediately realize that this case is particular. This case here is particular because what does it happen if you take a light beam and you slightly increase the angle I? The angle T will be increased. You increase still more the angle I. This angle will be increased, and you will reach a condition of the incident angle such that the refraction angle T will be pi over 2. Okay? So it exists one angle, I, let's call limit, such that the transmitted angle is pi over 2. Okay? Then what do you have? You have that the sinus of this limit angle divided the sinus pi over 2 will be equal to n2 divided by n1. Okay? The sinus here is 1. And then how much is this limit angle? It is the arc whose sinus is the ratio of the two refractive indices. Okay, if you know the two media and you know their refractive index, say you know n2 and you know n1, you calculate the ratio, you calculate this arc sinus, and you get this limit angle. Okay? Now, what does it happen if the incidence angle gets larger than this limit angle? If it gets larger, this beam should be pushed to a larger angle, but it can't. It means that there is not any more refraction. And if you have light above the critical angle, this limit angle, so if you have light coming at a larger angle, I could have designed better. Gosh. Then there will not be any refraction here, and you will have the light is totally reflected back. Okay? So when you have a situation like this, n1 and n2 less than n1, if the angle is smaller than this limit angle, and this limit angle is also called critical angle. If the angle is lower than the critical angle, you will have a transmission and reflection. I didn't design here the reflection, but it is always there. When the angle gets larger than the critical angle, you just have reflection and you have no transmission in the second medium. Now, if you look at this condition here, you understand that in the first case, when N2 is larger than N1, you see here, if N2 is larger than N1, this is larger than 1, and this solution doesn't exist. There is no critical angle. So if you have light coming from a lower refractive index to a larger refractive index, you will never have this process of the critical angle. Okay? Now, what does it mean? It means that, for example, if you have an interface between air, water, and air, air is more or less the same as vacuum, so it's got a refractive index 1. Water has a refractive index of 1.33. And if you have light, you can calculate this critical angle, and this critical angle is the arc whose sinus is 1 over 1.33. Can one calculate this with his pocket calculator? No, in degrees. Okay. Looks like it should be 42. Is it correct? Okay, 48.7. So this is the critical. Ah, no, that's true. Air, water is like that. You're right. So what does it mean? That if you are at the seaside, okay, if there is, this is the bottom of the sea, okay, if this is water, if this is air, okay, if you have a lamp here that is emitting light, okay, the optical rays that is going in this direction has a 0 incidence angle, so it has a 0 transmittance angle. The optical ray that is going in this direction here is being refracted like that. Okay, the optical ray that is going here is being reflected like that. The optical ray that is going at an angle that is the critical angle is being refracted like that. Okay, and the optical ray that is going like this will be totally internal refracted. So here you have total internal reflection. While here, for example, in this position, you know, part of the light will be transmitted and part will be reflected in the same year and the same year. Okay? So light that is emitted in this cone, a cone that has an angle of the critical angle will be sent in the outer world. Okay? Light that is being sent outside this cone will remain inside the medium. Okay? And will be trapped inside the medium. Now, since optics is reversible, so you can invert the direction of the light rays, what does this mean? It means that if you have light coming at a grazing incidence here, like this, it will be refracted here. Okay? If you have light coming at a certain angle here, it will be refracted inside the cone. Okay? So it means that if you are an observer that is here, a scuba diver that is on the bottom of the sea, resting like this, the light coming from the outer world will come to you through a cone. You will see the whole world inside a cone. Outside, you don't see anything. Okay? So, and you go back to this picture, this from the Nemo cartoon. Do you remember Nemo? Nemo. Wake up, Nemo, wake up, you have to go to school. And there is the sun and the sea, no? They look on top of and they see a white disk on the surface of the sea. That white disk is where you see the light coming from, in a cone. Okay? And this is due to total internal reflection. That's clear for you? If you are a scuba diver, did you ever scuba dive or dive a bit? And you are in the sea and it's a very good day with a very flat sea, and you look on the side. What do you see on the side? You see like a mirror. You see a reflecting mirror. Because if you are, if you are a scuba diver and you are watching in this direction, if you are sending light in this direction, this will be totally internally reflected, but it is the same on this direction. So what is outside this cone for you is the total internal reflection coming from inside the sea. Okay? And everything is governed by the refractive indices of these two media here, water and air. Okay? Now, if you have, say, glass air interface, then glass has got a refractive index that is about 1.5. Air has a refractive index of 1. Can you calculate this critical angle? How much is this critical angle? How much is it? Pocket calculate. It's about 42 degrees. Am I right? 42 degrees. So it is 42 degrees. So if you have a slab of glass, a sheet of glass, okay, say this. Okay. Then light that is here, and it is propagating, if it is propagating at an angle larger than 48 degrees, will be trapped in the sheet. And you get a waveguide. If it is a cylinder, you get an optical fiber, and so on. The basic is the so-called, this phenomenon is called total internal reflection. Okay? So, if E is larger than this limit angle, or we call it also critical angle, or also total internal reflection angle, then you get total internal reflection. Okay? And this happens only under these conditions. If N1 is larger than N2. So if you go from a medium with a larger refractive index to a medium with a lower refractive index. Okay? Now, one could ask, okay, but what you said is for a flat, infinite interface between two semi-infinite media. But what does it happen if instead of that, you get an interface like this between two media? Locally, you can approximate the interface with a flat interface, and locally the Snell law will be valid. Okay? And we shall see that locally, light coming at a certain angle will be refracted at a certain angle. This will make that if you have a wavefront, say for example, a flat wavefront coming towards a non-flat interface, locally you will have to apply the Snell law point by point. It is very complicated, but it can be done. We shall not do it, except in very simple cases. Okay? But the concept is that today we wrote this law that is important for us. And it must be in your mind, and that there exists an angle that we call it total internal reflection angle, that is the arc sinus, the ratio N2 and N1. And if E is larger than theta, the total internal reflection angle, then there is no refraction. Only reflection. Okay? Now, the Snell law doesn't tell you anything about, let's say, the intensity of the incident light, the intensity of the transmitted light, and the intensity of the reflected light. It doesn't tell you anything. So the Snell law only relates to the angles, but you cannot, with the Snell law, tell how much percent of the incident intensity is reflected back and how much percent is transmitted. Okay? These relations are given by the so-called Fresnel formulas. Since today we told many things, and it is 1842, and the Fresnel formulas deserve some attention because they are very simple. We shall write them down, but then we have to discuss a bit them. We stop here and we start next time with Fresnel formulas. Now that we gave the Snell law, we are ready to go into the laboratory, because in the laboratory we shall make measurements the first day on the Snell law and the total internal reflection, and we will evaluate how it doesn't work practically. And I think that the next laboratory will be on the next Monday. No, not the next Thursday, Thursday of the next week. Okay? in the afternoon. Why in the afternoon? Or maybe in the morning, depending. I want to know what is your timetable before and after my lectures. So, for example, today, before my lectures, you get electromagnetic fields liberty, no? I think. And what about Thursday morning? What do you have in the morning? After my lecture, again, liberty. Herrera, okay. Because this laboratory will not be here. We will be in the Via Scarpa buildings, and you have to reach them and to come back here in time for the lecture. So it's 2.5 hours. So we could start at 9, finish at 11:30, and then you come here for the lecture of Herrera. When does Herrera start? At what time exactly? Noon? On Thursday, you don't have? Herrera, no, Caputo. And when does it start? At noon? Exactly at noon? But he starts effectively at noon? Yes. Okay. And on Thursday morning, can you come at 8:30 to that place? So we do like that. So now I will arrange the timetable and give you the date exactly. We start at 8:30, that you finish at 11, then you have 1 full hour to come here. And that's enough, I would say. Now, wait, I have to think about it. But as soon as possible, okay? Okay, are there any questions? Next Thursday, we meet in hall number 3, okay?